Hello everyone. Welcome back to this lecture series on design of RCC structures. This is a lecture 19 in which we are going to discuss the design of short columns subjected to uniaxial bending. In the previous lecture, we designed axial loaded short columns. However, in real structures, columns rarely carry pure axial load. Due to the eccentric loading, the beam reactions and the frame action, the columns are subjected to axial load combined with a bending moment. Today, we study the design of short columns under uniaxial bending, which is one of the most important and practical topics in column design. So, when a column is subjected to axial load along with a moment about one axis alone, it is called uniaxial bending. This means bending occurs only about the major axis or minor axis. The compression stress may vary linearly across the section, and one side may have higher compression than the other. With this background, let us solve this numerical example. We are asked to design the reinforcements for column of size 300 mm by 500 mm, which has been subjected to an ultimate axial load of 1000 kilonewton along with the ultimate moment of 250 kilonewton meter. The grade of concrete is given as M25 and the grade of steel is given as Fe415. So the first step of solving this numerical example is identifying the nature of the bending. So here the moment is specified with respect to major axis. Since 500 mm is the larger dimension, bending occurs about that axis, which means the compression zone develops along the larger depth and the stress distribution varies across 500 mm depth. Now let us start with the non-dimensional parameter. Since we are going to use the interaction charts as prescribed by the limit state method, we are going to find the non-dimensional parameters. It starts with the Pu by FCK BD and Mu by FCK BD square, wherein Pu is the ultimate axial load, Mu is the ultimate moment which will be acting on the column. FCK is the characteristic strength of the concrete, B and D are the cross dimensions of the column. So substituting all the values, we'll be getting Pu by FCK BD as 0.267 and Mu by FCK BD square as 0.133. So with these two, assuming an effective cover of 50 mm, making the ratio D dash by D. D dash represents the effective cover which has been assumed as 50 mm and capital D is the width of the section. That is what is the axis which has been taken as the critical one, that is 500 mm. So you'll be getting the ratio as 0.1. So with this 0.1, for a grade of Fe415 steel grade and D dash by D of 0.1, and we are going to assume the reinforcements which are to be provided equally on all four sides. Let me assume that I am going to have a column like this. If I am having a column like this, whatever the number of reinforcements if you are providing, all the sides it should have the same numbers. Let me have something like this. In this case, this side we have 3, this side we have 3, this side we have 3, and this side also we have 3. It's not like only with respect to the numbers as well as the area of the reinforcements also. So once going on with the SP16, under the chart number 44, which is being provided for Fe415 grade steel and with the D dash by D ratio of 0.1, we are going to have this condition also, that is reinforcements which are to be provided equally on all four sides. We'll have a chart which has been available, which has the y-axis as Pu by FCK BD and x-axis as Mu by FCK BD square. And we will have series of curves will be available. So each and every curve, this is the first curve represents P by FCK of 0 and the second curve represents P by FCK of 0.02. Likewise, as an increment of 0.02, this ratio will be available where P represents the percentage of the reinforcement and FCK is the grade of concrete. So now we calculated the PU by FCK BD and MU by FCK BD square. So since these two values are known, get the values. For example, that we already calculated PU by FCK BD is 0.267 and MU by FCK BD square is 0.133. So just go with this curve, that is PU by FCK BD, I think 0.267 and MU by FCK BD square 0.133. So intersect these two things, you will be getting near to one curve. Most of the cases it may not be coinciding exactly with the curve. Let me assume the curve is this one and this one. In between only this intersection point has been lying. Let me assume this is 0.02 and this is 0.04 in the sense. Make some similarity between these two and get the value of this P by FCK. Right. So in this case, for PU by FCK BD of 0.267 and MU by FCK BD square of 0.133, we are getting the P by FCK as 0.09. Now from this, the percentage of the reinforcement can be calculated by multiplying this 0.09 with the FCK. That is, P is equal to 0.09 into 25, we'll get 2.25. And this has to satisfy the minimum condition of 0.8% with a maximum percentage of 6%. This is P minimum and this is P maximum for a column. So these two has been satisfied because this 2.25 is between 0.8 and 6. Now for this one, we can find the area of the steel required. That is, AIC will be equal to P into BD by 100, where P is the percentage and B and D are the cross dimension of the column. So substituting all the values, we'll be getting the area of the steel required as 3375 mm square. And since we already assumed that the reinforcements are to be provided equally on all four sides, so the number of reinforcements, whatever we are going to provide, should be in the multiples of 4. So let me assume I am going to provide 8 numbers of 25 mm dia bars with the 3 bars equally on all 4 sides, which will provide the area of the steel as 3927. Right. So now coming on to the transverse reinforcement. So similar to the axial loading, this uniaxial bending as well as even the biaxial bending also will have the same criterion which will be followed in order to design the transverse reinforcement. So going on with the tie diameter, we have two conditions are available. One is 1/4 of the maximum longitudinal diameter bar and the second one is 6 mm. So we need to provide greater than these two values, maximum of these two values. So we are provided with the 25 mm diameter bar. So 25 by 4, you'll be getting 6.25. So we are supposed to provide the lateral tie diameter of greater than the maximum of these two. So here the maximum is 6.25. So we need to provide greater than this 6.25 and we don't have 7 mm bar in practice. Therefore, we are providing 8 mm dia lateral ties as the transverse reinforcement. Now moving on with the spacing. Spacing is being governed by 3 different factors. One is the longest cross dimension. Second one is 16 times the minimum longitudinal diameter of the bar. And the third one is 300 mm. So minimum of these two should be provided. So in this case, the maximum dimension is 500 mm. And 16 times we are provided with the same diameter of the bar. So in that case, it will be 16 into 25, which comes 400. And the least condition is 300. So in that case, the minimum of these three will be 300 mm. Therefore, we are going to provide the spacing as 300 mm. Therefore, this ties will be provided in the form of 8 mm dia ties at 300 mm centers. So this is the first case in which we assumed the reinforcements, the main reinforcements are to be provided equally on all the 4 sides. Let me have the reinforcement details. You can see we are provided with the 8 numbers of 25 mm dia bars, 4 at the corners and 4 at the middle of the sides. So 8 reinforcements being provided on the periphery of the column, and this being connected by means of the lateral ties in the form of the staggered one, and that has been provided with 8 mm dia bars spaced at 300 mm centers. So this is the reinforcement details. Now the second case is, again we are going to assuming an effective cover of same 50 mm with a d dash by d ratio of 0.1. There is no change in this one. But in this case, we are going to assume the reinforcements are to be provided equally on 2 sides, not equally on all the 4 sides. So for this case, that is for Fe 415 grade steel and D dash by D ratio of 0.1, reinforcements provided equally on two sides. We are going to have the chart required to this one is belonging with the chart 32 of SP16. Now, with this chart, for the same PU by FCK BD and MU by FCK BD square, we'll get the same sort of a nature of the graph only. Get the value in the y-axis and this one on the x-axis. Get the 2 points meet intersect at one point. Get the curve which is near to that intersection point. That will give the P by FCK value. In this criterion, we found the P by FCK value of 0.07. So from which P value has been calculated as 1.75. And again, this value is greater than, 0.8% and less than 6%. The minimum and the maximum percentage of the steel requirement for a column. Right. So from this, the AC required will be calculated as 2625, whereas in the previous case, it went up to 3000. Right. So we are providing again here in this case, the reinforcements are to be provided equally on two sides. In that case, the number of reinforcements what we are going to provide can be in the multiples of 2. So for which I am assuming the same diameter of the bar, that is I am going with the 6 numbers or 25 mm dia bars. In that case, we are providing 3 bars equally on two sides. So that the area of the steel provided will come as 2945, whereas the requirement is 2625. And regarding the lateral ties, there is no difference whether we are providing with the reinforcements equally spaced on two sides or four sides. It remains the same thing. Right. And we are going to provide 6 numbers, 3 on either side. Right. So in that case, you can see these two sides are equally provided with the numbers and these two sides are equally provided with the numbers. That is what is the difference between equally provided the reinforcements on 4 sides as well as on 2 sides. Okay. So here, this reinforcements ensures that the column can safely resist the axial load, moment capacity is to be adequate, and the compression failure is avoided. And regarding the purpose of the ties is to prevent the buckling of the longitudinal bars. It will confine the concrete core as well as improve the ductility. Here the detailing is as important as calculation because improper detailing may lead to premature failure, buckling of bars, as well as resulting in reduced strength. So practically this uniaxial bending occurs in edge of the columns, edge columns, normally in a building where the columns being provided on the edges and columns supporting eccentric loads as well as wind and seismic conditions. In real practice, we know pure axial loading is extremely rare. In the next lecture, we will extend this concept to columns under biaxial bending. Thank you.